Hello everyone. This is Ravindra, PhD student in Material Science and Engineering at University of North Texas. I'm glad that IEEE has given me this opportunity to present my work virtually in the situation of pandemic. So I'll just start on to my presentation. So the topic of my of today's presentation is electrons and hole doping of two-dimensional molybdenum disulfide to enable the heterojunction nanoelectronic devices. And as you see, my contact information is my email ID is already displayed, and I am currently pursuing my PhD under Professor Anupama Kaul. Name of a lab is Nanoscale Materials and Device Laboratory at University of North Texas. So let's start. So just to start with a brief review of our expertise, our lab. So what we do in our lab is we synthesize nanomaterials. As you see, from 2D, 1D, 0D. I work basically on 2D materials, mainly black phosphorus and transition metal dichalcogenides. And we have several synthesis techniques available in our lab and as well as our research facility. We have in-house PVD and CVD inkjet printing for additive manufacturing, and we have glove box to store air-sensitive materials. And we also use UNT clean room shared facility to fabricate devices. And we also have several characterization tools to measure the electrical IV, the resistance temperature data, the CV and CF graphs. We also have tunable lasers for temperature dependent optoelectronic properties. And we also have temperature dependent Raman and PL measurements along with TORS and UV-based absorption spectroscopy. And obviously, and we also use the UNT shared facility to use XCM, XRD, and SPS techniques. And the devices which we fabricate are mainly nanoelectronic devices, photodetectors. We also work on flexible electronics, solar cells, and several others. So these are some of the recent publications which came out from our group. So we are featured in NPJ. It was published in NPJ 2D materials and applications. That was based on additive manufacturing of perovskite. And another of our publication was featured in ACS Applied Materials and Interfaces. And we also have another publication based on quantum multibody interactions in WSE2 from our group, featured in ACS Chemistry of Materials in 2019. And one of our articles was also got selected as a back cover image in Journal of Material Chemistry. And one of my publication was also published in Journal of Vacuum Science and Technology as a part of AVS conference. And we also published on additive manufacturing of 2D materials on biocompatible MoS2 inkjet printing photodetectors. And we also published an article recently on the organohalides 2D layer perovskites in applied materials and interfaces. And also recently, one of our article got selected as a supplementary cover image in ACS Applied Materials and Interfaces. And one of our articles on androhydral dope graphene was also selected for the back cover image of Journal of Materials Chemistry C. So coming on to my presentation for today. So I'm going to start with a brief review of doping strategies in 2D materials. So MoS2, as we know, is a layered two-dimensional transition metal dichalcogenides. So it has a layer dependent band gap, uh, and also it has thickness which varies with number of layers. So as you can see, the band gap in MoS2, it changes from both the magnitude and the type changes with number of layers. So as you see in the figure over here, there's a transition from indirect to direct band gap as we move up in the number of layers. So basically the direct band gap occurs at around 1.9 eV and indirect band gap at around 1.3 electron volts, which is the band gap range for typical MoS2. And it also changes with number of layers. As you see, for monolayer the band gap is more direct, and as you increase the number of layers it turns to indirect. So we see there are several doping techniques which has been already employed, and techniques employing surface functionalization, plasma treatment, surface adsorption, work function engineering for contact metals. They have proved to be not very effective because the contact resistance was still pretty high in by applying those uh, doping techniques. Also the doping is important because it also enables bipolar carrier transport, which can enhance device performance. That is, you can have both N and P type conduction in the same devices. And some of the doping techniques which are which have been employed recently, and which has diminished the uh, cons of the other doping techniques as mentioned are the substitution doping, doping by charge transfer mechanism, by intercalation, and the electrostatic doping to induce charge carriers. So over here, we are mainly our work is mainly focused on the substitution and charge transfer doping, and also because of the inherent Schottky defects already present in the transition metal chalcogenides, it makes easier to dope these materials employing these techniques. And also because of the ultra thin nature of 2D materials, we cannot employ the conventional doping techniques such as ion implantation, which is typically used in silicon semiconductor industry. And also because it's the basal plane is exposed completely in case of 2D materials, it becomes easy to dope these materials by charge transfer and substitution processes. So starting with the device fabrication and doping. So the way we fabricated our device is we started with we started with the bulk MoS2 layer, and we exfoliated it several times by Scotch tape techniques and transferred it on to the silicon dioxide substrate. And we use electron beam lithography to pattern our contacts, uh, which were titanium gold, 10 nanometer titanium, 100 nanometer gold contacts, which was deposited and lifted off. And once we made the contacts, we followed the two doping processes, one for N-type doping and another for P-type doping. So for N-type doping, we immerse our device in 1,2-dichloroethane and soaked it for 24 hours. So the way doping happens in this is by substitution of sulfur vacancies by chlorine atoms, which by substitution there is a broadening of there is merging of the broadening and merging of the bands, which reduces the band gaps and dopes the semiconductor. And in case of UV ozone, we place our device in the UV ozone chamber and expose it under UV ozone for about 30 minutes. And doping occurs as a result of redox reaction due to solubilization of O3 and large oxidation potential. That is, when you expose it to the UV ozone, there is always some moisture present on the surface of your sample out of the 2D materials, and which facilitates absorption of O3 molecules. And once it's absorbed, it undergoes the redox potential due to large oxidation potential difference between O3 and MoS2, MoS2 has a highly negative redox oxidation potential compared to MoS2, so it gets reduced pretty easily, and the charge transfer takes place from MoS2 to O3, and that's how it becomes p-type after doping. And here we also the figures shown over here A and B are the optical images taken at 100x after the fabrication of contacts. The first one shows the device before immersion in 1,2-dichloroethane, and on the right it shows device before immersion into before exposing it to UV ozone. As you see, the contacts are pretty clean, and the materials was contacted well using the fabrication technique employed. And what you see over here is also the optical optical images on the Raman and PL spectra of the samples before UV ozone doping, before 1,2-dichloroethane doping, and before UV ozone doping. So what you see is both of them, the difference in the delta K value from the Raman spectra for both of them is less than 26, between 18 and 26, which implies that the device we fabricated were a few layers MOS2, and you can also see from the photoluminescence spectra obtained, and it shows the band gap of around 1.8 eV for both of them. However, we see that the device which was fabricated, the second device which before UV ozone, which was exposed to UV ozone, has a sharper PL peak and lower full width half maxima, which means it has higher crystallinity compared to the one which was doped before one by 1,2-dichloroethane. Those were just the inherent attributes of the flake. So coming on to the electrical characterization. So the figures over here shows the two terminal electrical measurements before and after chloride doping. So the figure on the left was set between -10 to 10 volt range, and figure on the right shows the same graph but in the narrow voltage range, that is -1 to 1 voltage range, and the measurements were taken with lights off. And as you can see, there is some significant improvement in the electrical signal, at least by half an order of magnitude, after doping by 1,2-dichloroethane, that is N-type doping. And also the trend of higher negative current continues to remain before and after doping. Also another thing you see is there's significantly higher currents after doping by 1,2-dichloroethane, even at lower voltages, which you can see on the graphs on the right, which is attributed to the N-type doping effect for the already N-type MoS2, inherent N-type MoS2. And the next graph shows the same plot but for before with lights off for before and after UV ozone doping. So what you see over here is on the left, the current levels before and after UV ozone doping are significantly higher than the currents before and after 1,2-dichloroethane, which could be due to the better crystallinity of the sample as shown in the PL peaks earlier. And also another thing you see is there's decrease in current levels measured after UV ozone doping compared to the chloride doping, which could be due to charge scattering induced by excessive carrier concentration, which would be the p-type carrier concentration in this case. Next, I'll talk about the optoelectronic characterization before and after chloride doping. So here we'll use the broadband lights, and we do two terminal measurements before and after doping. So the figure on the left shows this plot in two-terminal plot in -10 to 10 voltage range before and after chloride doping, but in presence of broadband lights. And on the right shows the same plot in narrow range. So what we see over here is there is drastic improvement in the electrical signal of the sample before doping in presence of broadband lights compared to the measurements with lights off. as it is clearly visible. Also, the current levels in the presence of broadband lights remain unaltered compared to the electrical measurements in dark after chloride doping. If you look back to the slide, you'll see that the current levels are not changing much after chloride doping, which in presence of broadband lights, which could be due to because there is some surface molecules absorbed on the surface, which might be preventing lights uh, to penetrate further inside. That's why the electrical signals remains the same almost before and after doping. Also, another thing you see is there is the electrical response in terms of broadband lights before and after chloride doping points the difference in currents between them is much lower at lower voltages, which increases with increase in voltage, which you can clearly see in the comparison of narrow voltage range and the full range sweep. So now we'll talk about the optoelectronic characterization before and after UV ozone doping. So again, the figure on the left shows the full range, and as you can see, the arrow pointing out shows the narrow voltage range of the same measurements before and after UV ozone doping in presence of external simple broadband lights. So what we see over here is there is suppression in currents after the UV ozone doping in the negative voltage range before it reaches the compliance current of 100 microamps, which was set in all the devices in order to prevent the device from getting overheated due to excessive due to excessive power dissipated. And the suppression is much higher at the positive voltage range in the presence of broadband lights. Also, we see that broadband lights improve the electrical signal of the sample before 1,2-dichloroethane doping and slightly suppresses it after UV ozone doping, which could be because of the interaction of the light with the defects, which would be suppressing those current levels. So to summarize, we have first ever demonstrated the effects of 1,2-dichloroethane and UV ozone doping and broadband light source on the two-terminal measured electrical behavior of mechanically exfoliated and electron beam lithographically patterned MoS2 flake with titanium gold contacts. Also, the doping in 1,2-dichloroethane is due to the vacancy substitution, and by UV ozone is due to difference in chemical potential. Also, we see that the difference in electrical response before and after doping by the two dopants is because of the difference in doping mechanism uh, between them. And there is increase in the electrical signal after 1,2-dichloroethane doping attributed to N-type doping effects. And the decrease in electrical signal after UV ozone doping is attributed due to the scattering by excessive charge carrier concentration. So I'd like to thank you all for listening to this presentation, and feel free to contact me on the email ID provided on the beginning of the slide. And we'd like to thank our sponsors because of whom we were able to conduct this research. We'd like to thank Office of Naval Research, NSF, UNT, and other sponsors, and also all my lab colleagues. Thank you so much for listening.